So what we did last time was basically started off with this chapter on trying to find approximate numerical solutions to the weak form. And if you remember, we said that we are essentially trying to solve these types of strong forms, which for these, usually we cannot find exact solutions. So we converted them to a principle of virtual work form of the weak form. And this is the one that we will approximate with numerical methods. We can do approximate integrals and so on to try to find approximate solutions. In particular, for the one-dimensional problem, this was the weak form that we were going to work with. So the idea really is that this weak form is a function of the stress function, which itself is a function of the real displacement. So think of this as the real displacement function, and this is the virtual displacement function. You have this integral where we will plug in some approximations for the real and the virtual displacements, and we will get some integral that we can actually evaluate with numerical methods, and we'll see how to do that today. So this was the overall big picture that I've been stressing you all to try to keep in mind. And last time where we were was to try to see what kind of approximation functions to pick for this real displacement and virtual displacement. So last time we said that let's make sure we understand what the conditions are for real displacement. We said real displacement must be in H1 for PVW weak form, correct? Real displacement must be in H1, which means that anything that is not discontinuous, any function that is not discontinuous would work. Those are H1 functions. And in addition, the real displacement must satisfy the essential boundary condition. That is, if I'm given a displacement at a point of the body, then the real displacement function that I assume must satisfy that condition. The weak form itself has no way of satisfying the essential boundary condition for you. That's why we have to pick functions that actually do satisfy that condition. So the way we constructed that was we picked one particular function called H0 that started at the correct value U0, right? If this left end is displacement U0, then that particular function is U0. That's the one that helps us satisfy the essential boundary condition. All the other functions, H1, H2, and so on up till Hn, they all start from 0. So when I add them together, the result is that the approximation for the real displacement will have the value U0 at x equal to 0. Hopefully you all see that. And the expression that we ended up for the real displacement was H0 of x plus a vector of unknown coefficients. These are the unknown coefficients that we will solve for finally, times a vector of functions of x which are known to me or which I have picked and which I have handpicked to be able to approximate the real displacement. So that gives me an approximation for the real displacement. And similarly, last time I think I glossed over this a little bit, but some of the examples of these H functions that people can pick are in the space of polynomial functions or trigonometric functions. Sometimes, very often, what people use is the finite element approximations, which is actually piecewise polynomial, and we'll take a look at that later in this chapter. Most commonly, we'll use either a polynomial or a trigonometric functions for all these H1, H2, H3, all these HI functions. Okay, so that's the real displacement. What about the virtual displacement? We said last time that we can use the same space of functions. The same HI functions that we used for the real displacement is what we can use for virtual displacements as well. Keep in mind that we need to we are approximating this real and virtual displacements just to plug it back into the weak form, the G functional that I introduced, right? And finally, what we want to do is to take that G functional and try to set it to 0 for all possible U bars, for infinitely many U bars, right? That is not possible for us to do. We cannot make, we cannot ensure that this this function will go to 0 for all possible u bar functions in this. So what we said, okay, since we cannot make it go to 0 for all possible u bars, let me pick a subset of u bar functions for which I will make sure that this function goes to 0 for that class of functions. What is that class of functions? I'm saying that that class of functions will be the same hi functions that I'm using. Any linear combination of these functions, there are still infinitely many u bar functions in this class. And for any linear combination of those functions, my g functional will go to 0. And we said the other condition on this u bar was that indeed it has to be in h1, just like the real displacement. Virtual displacement also has to be in h1. And it must satisfy the homogeneous essential boundary condition, which means that this h0 term will not be there in the virtual displacement, that it will actually be 0. We want all our functions for the virtual space to start at x equal to 0 if real displacement is specified at 0. We don't have that u0 for the real displacement in here. That was the homogeneous essential boundary condition that we said. And if I were to write that in a matrix form, I could write that as a1 bar, a2 bar, so on up till an bar times a vertical vector of the same functions h1, h2 of x up to hn of x. Okay. A quick note here, in this particular case, we use the same h functions that we used for the real displacement. Sometimes people do use different shape functions for the virtual displacement and different shape functions for real displacement. Those types of methods are called Petrov-Galerkin methods. This particular choice that we made is called the Galerkin method or the Bubnov-Galerkin method. I should also mention a term that I just used. Sometimes these are called shape functions or even basis functions. So, or approximation functions. These are all sort of equivalent names for these set of functions that people use. Okay. So at this point, I have some approximation for the real displacement and some approximation for the virtual displacement. What I'm ready to do now is to plug in these approximations into my weak form. If you remember, this was the weak form that we had originally developed. G functional is a functional of real displacement and virtual displacement, which was given by this. This is the PVW weak form that we had originally developed, right? I've just spaced it out so that I can add some more stuff here, but it's the same weak form. What we'll do now is we'll plug in these approximations, and the objective of that would be to try to find these unknown parameters. So let me actually plug in this first. The approximation for u bar, the virtual displacement, what is that? A bar transpose times h vector x, right? So keep in mind what this looks like is a horizontal vector and times a vertical vector. These a bar coefficients are arbitrary. We don't care really what their value is. We have to make sure that this g function goes to 0 for arbitrary, all possible choices of a bar coefficients. Times c as it is, and then the approximation for u, and actually I need the prime here as well, because clearly derivative of u bar, if I take derivative of u bar, a bars don't depend upon x, this h does depend upon x, so essentially this is the vector of derivatives of the x function. Okay. And then I also have on the right hand side, I'll write it as h0x. I'll need some more space, I think. H0x plus, I'll write it slightly differently, h prime vector x times and transpose and times the real vector A and square bracket close. So all of that thing in the square bracket, I hope you can see that that's u prime, du dx. And actually I need a prime on this h0 as well, right? So I have my approximation for u bar prime and I have my approximation for u prime. All I've done is I've plugged in those approximations in this term. I'll do the same thing for the boundary force term. So u bar here is equal to a bar transpose times h vector x and the body force function b and minus the boundary term. That would be, I'll write that still in red, a bar sorry. Okay, so a bar vector transpose and h at the value L, this would be a vector and that UL is in this parenthesis. All I did was substitute my approximation into the weak form, okay? And now the rest is basically just algebra. But let me state the problem that we are trying to solve now. We want to make sure that this functional went to 0 for all possible u bar. Instead, what we are going to do is to make sure that this functional goes to 0 for all possible a bars. And I'll make that red as well. So for all possible coefficients of the virtual displacement, we will make sure that this goes to 0. And we are going to try to find the real coefficients a this vector, which is equal to a1, a2, so on, an. These are the unknown coefficients that we are trying to find. So we'll find a coefficients such that this g functional goes to 0 for all possible a bar coefficients. And that, when I do that, that would be an approximation of the fact of the principle of virtual work form or the weak form that will make sure that this would go to 0 for all possible a bar or all possible u bar functions within that small space. Okay, and this particular problem is called the Galerkin form of the weak form that we had originally developed. And maybe on the previous page, at the bottom, you may see here we are taking the principal work form of the principle of virtual work form of the weak form. We are making an approximation now on G of on this virtual work form, and ultimately we will want to end up with equations like this, which we know can be easily solved on a computer. Okay, all right. So let's see how do we simplify this. So I think this is something that I've already mentioned. I won't go into much more detail about that. So upon simplification, which I've already sort of laid out the steps for you, the idea is that I'll pull out these a bar transpose functions. These were red originally. I'm not going to distinguish colors anymore. These were a bar transpose, the virtual coefficients of the virtual displacement. This is the coefficient of the real displacement. What is left inside is C times H prime transpose. Okay, hopefully you can convince yourself that this is what is left from the previous page. And then you have one term that accounts for the fact that there is H0 in the real displacement. There's another term that accounts for the body force term. And there's another term that accounts for the traction term at L. So all of this entire thing right here is what we are going to call A transpose KA. And this term in the square brackets, as I mentioned also in the review session, that is the stiffness matrix or K term that we normally obtain in structural analysis. All of this term you can clearly see, you can pull out A bar transpose out to the left, and whatever will be left in the curly brackets would be the vector F. And if I if I rewrite this entire big matrix equation using matrix symbols, then I would get take out A bar out common, and in the brackets we would have Ka minus F. And this is an exercise I think that this is also there in your homework problem too, and something that we did in that Friday review session as well. You should be able to see that this is a vertical vector H. This H transpose is a horizontal vector. So clearly a vertical vector, this is a vertical vector, and this is a horizontal vector. So clearly the outer product of vertical times horizontal will give me a matrix, which is what this stiffness matrix. And all of these things are vertical vectors. So this is a vertical vector of derivatives of shape functions. Same thing here, a vertical vector, a vertical vector. Everything else is a scalar in this. So that's how we get the right hand side to be a vector F. And now the statement is find real coefficients. Find real coefficients A such that this entire function goes to 0 for all A bars. For all A bars, which is very easy to do, because if you can solve this part of the equation, then no matter what value of A bar you have, this functional will go to 0. Irrespective of the value of A bar, this function will go to 0 if you solve this part of the equation. And in this particular case, we have written this, what we have used, we had a linear problem. So we ended up with a linear system of equations, of matrix equations. K, A, where A is coefficients. Normally in structural analyses, these A coefficients turn out to be degrees of freedom, right? And as I mentioned, if you have a non-linear problem, then this equation itself would be a non-linear equation, which we normally denote with a residual function of the unknown displacements. And ultimately, the equation that we would solve would be simply by taking K inverse times F, we would get the real coefficients A that we wanted to find. And as soon as we get the real coefficients A, we go back and plug it into our original approximation for the real displacement. As soon as we find this H, then I know an approximate displacement of the original bar. Okay, so that would be the overall logic of how we will solve these types of problems. Just a side note, for non-linear problems, the residual function, as I said, it may not be a linear function. This K times A, this is a matrix times A vector. This is a linear function of the unknown coefficients. For non-linear problems, this can be a possibly non-linear function which denotes internal force. Ka is the internal force in linear problems. So if you have a non-linear problem, you have to do iterations to solve it. And again, if you're interested in this, we can definitely talk more about it, but I won't go into too much detail about non-linear problems of how to solve these equations. We will focus on solving these linear equations for which the solution is simply K inverse times F. And I'll show you an example of how to do this now. All right, so here's an example. Left end is fixed or a displacement specified, where the displacement is specified to be equal to some u0. The body force is this function b naught sine x pi over L, and what that looks like is this half sine curve. In addition, we have some traction at the right end. So the governing differential equations are pretty straightforward, cu prime whole prime plus p. And note that c is not varying, c is constant. So actually you can take the derivative inside, cu double prime plus b equal to 0. On the left end, I have a displacement boundary condition, an essential boundary condition. Maybe I'll write that right here. This is an essential boundary condition. And on the right end, it's a traction or a natural boundary condition. And hopefully you are all comfortable now that traction is equal to stress acting on the normal. That's what this traction boundary condition is on the right end. Let's assume area of cross section is 1. So TL, actually we didn't bring in that, but it doesn't matter what area of cross section is. We know how to solve this exactly. We can find the exact solution. Actually, I'll make a comment here as well. The way we found exact solutions in the previous examples was to do integral sigma, d sigma is equal to integral b dx plus c1, some constant. And you use c1 and c2, the constants you found by using boundary conditions, right? Here, I'm taking a slightly different approach. I'm saying that integral d sigma, I can do that between sigma L and sigma x. And I'm avoiding that constant C1 completely. Since I know the stress at the right end, because I know the traction at the right end, I can integrate from any point x to L. So if I take a finite integral, not a definite integral, sorry, not an indefinite integral, between sigma x to sigma L, that's what I get here. And integral of x to L b dx, and then I don't need a constant of integration. So in this particular case, if you evaluate that integral, then that gives me an expression for the stress at any point x along the bar, which is given by this long expression. And similarly, if I integrate now, once I know stress, I can find displacement. If you remember, we said integral of du was equal to integral of sigma x over c dx, correct? And we have the constant c2 there, which we again found by boundary conditions. But I'll again avoid that constant by doing a definite integral between u0 and ux. So for the first integral for sigma, I knew sigma at the right end. That's why I went from sigma x to sigma L. But for displacements, I know the displacement at the left end. So I'll take the integral from the left to some point x in the bar. And that's what I'm writing here. Ux minus u0 is equal to 1 over sigma x integral dx, integral, a definite integral between 0 and x. Now I don't need a c2 here. And if I do that, I can find that u as a function of x is given by this expression. And you can verify with the other way as well. If you use C1 and C2, use boundary conditions to find those C1 and C2, you'll get the exact same expressions. Okay. The benefit of this expressions by doing these types of integrals is going to be clear very shortly when I actually show you the Matlab code to try to find these types of solutions. Okay, this is the exact solution. In general, of course, we will not know the exact solution beforehand. So let's see, when we actually follow our approximate solution method, we get some approximate solution. How does that approximate solution compare to this exact solution? Okay, so let's see how to do that. What we are going to do is to again use the principle of virtual work form of the weak form. And we are going to plug in our approximation for the real displacement. Remember, approximation for the real displacement was h0 plus a transpose times x. And this coefficients of these coefficients are the ones that we are trying to find. And the virtual displacement is simply given by a bar transpose x. These a bars could be anything for all a bar transpose, right? We don't care what these coefficients are, what the a bar coefficients are, we don't care about them. What we are trying to find are the real coefficients. All right. Now, if I plug that in, I know that we get A transpose times Ka minus F, where K is given by this expression and F is given by all of this expression. I think I'm missing H0 as well in this. So let me check. I think I've chosen const. Okay, so that's good. All right. So now the question is, how do I choose these H0 functions, H functions for this real and the virtual displacements? Okay. So what condition should the H0 function satisfy? I need to pick some functions. I want to find an approximate solution to this problem. So I need to pick some functions. I need to pick functions H0 and the functions Hi, H1, H2, H3, and so on. Okay. The only condition that H0 function needs to satisfy is that it has to be in H1, of course. But other than that, it has to have the value. It has to have the value U0 at x equal to 0, correct? What would be the simplest function that would do that? u0, constant function. For any value of x, the value of that function is u0. All right. So let's pick that. I'll say that h0 is equal to u0. And in particular, for h1, h2, h3, and so on, we are going to make the choice that this is equal to x over L to the power I. So h1 is x over L, h2 is x over L squared, and so on. Okay. What do these look like? h1 is x over L, this straight line. It goes to 1 at x equal to L. h2 is x over L squared, x over L cube, and so on. Okay. So what we also now need is the derivatives of these functions. If you look at the previous page, we had all of this function, all of this went to f. So we need derivative of h0, and we need the derivative of all these h functions. So let's see what those are. Can you tell me what the derivative for h0 is? 0. What is the derivative of hi? Okay. I times x over L I minus 1, right? And actually we need to have divided by L also out here. And actually, so wait, divided by L over I, L to the power I, because sorry, only L. Yeah, only L, not L to the power I. That's just chain rule, because if I take derivative of this, then I need to go back in and take derivative of this guy with respect to x, which would be 1 over L, right? So that would be the derivative of the hi functions. And now I can calculate my k, which is given by this expression. So I'll write that out in the matrix form. This would be, since c is constant, I'll put it out of the integral, 0 to L of the vertical vector, which looks like h1 prime x and so on up to hn prime x, and the horizontal vector, which is also h1 prime x all the way up to hn prime x, and dx. So we'd have to do this big integral. Let's say if I have 5 functions, h1, h2, h3, h5, there will be 5 cross 1 vector here, a 1 cross 5 vector here. That would give me a total matrix of 25 entries, right? 25 integrations we would have to do to find that matrix. But right now I am saying that it could be n. So n cross n square integrations we have to do. All right, but what we'll do is we'll find a particular entry at the ith row and the jth column. Can you tell me what the Kij, what would that Kij element, what would that integral be? C 0 to L of hi prime x times hj prime x dx. Do you agree? And maybe what I'll also do is replace that. So actually move that here. So it's a little bit tight here. I wanted to fit the entire example on one page, but so now I'll plug in the value there of integral of c times the derivative of hi function would be I over L times x over L I minus 1. Derivative of the hj function would be j over L x over L j minus 1 and dx. Okay. out of all of this, what are the constants? I, j, and L in the denominator, these are constants. So I'll pull them out, and what I'll be left with in the integrand, it would be x to the power I minus 1 plus j minus 1. Do you agree? X to the power I minus 1 plus j minus 1. And if I integrate that, I will get integral I, j, pulling that out of the integral. The integral of x to the power I minus 1 plus j minus 1 would be integral or x to the power I plus j minus 1 between 0 to L, and divided by L to the power I plus j. No, because I have already integrated that. So yeah, you're right. In here I would have x plus j minus 2, but if I integrate that, I get x plus j minus 1. And in the denominator, I would also get this term I plus j minus 1. That makes sense? Go ahead, Joe.
What about the additional L under the I?
Right, so I'm already pulling it out of the integral. This is L to the power I minus 1. This is L to the power j minus 1. So if I pull this out, this becomes L to the power I, L to the power j. That becomes L to the power I plus j. Okay? Make sense? All right, so this would be the expression that I would get. And if I calculate that between 0 and L, I should use capital L since I'm using capital L here. I would get L to the power I plus j minus 1. Do you agree? And then if I cancel that off with this guy, I would have only one L in the denominator. So that gives me C times I j over L I plus j minus 1. So that's a nice, neat expression. That gives me, that particular expression gives me the Kij entry of that big n cross n stiffness matrix. You plug in, you give me a value of I and j, I can tell you what that entry of that big stiffness matrix would be, right? So it doesn't matter whether there are 5 terms or 100 terms or 1,000 terms. I can calculate that stiffness matrix just by coding this up in Matlab, for example. All right, the same thing we'll do for F. F we know is given by this guy. Note here that I've already deleted the H0 prime term here because H0 prime is 0. So I got rid of that term already. We'll take this guy and just substitute that in here. So I'll write that off of this expression 0 to L H function H1 x H2 x all the way up to Hn x, that vertical vector, times body force function, which in this case is B naught sine of 2 pi, sine of pi x, x pi over L, dx, and plus the boundary term. So I'll write that in blue. So plus H1 at the value L, H2 at the value L, similarly Hn at x equal to L, and TL. Right? So hopefully you can see that what I've written out here is exactly the same expression out here, except that I have a prime here which should not be there. This should not be a prime. H times B, H. So there was a prime here that should not be there. And let me make sure on the previous page also I don't have that prime. Yep, I don't have that prime here. All right, so using similar logic, you can actually integrate this as well. And you can show that Fi would be given by this recurrence relationship, where this I is given in terms of I minus 2. And for that, you would need two initial values, I0 and I1. So using this recurrence relationship, so basically you would calculate I0, I1 then I2 would be given as 1 minus all of this I0. I3 would be given as 1 minus all of this I1, and so on. So you can calculate all of these values for Fi as well. Okay, that gives me the K, the stiffness matrix, and F, the force vector. And those two are the only things that I need to be able to calculate. Though I needed K, I needed F, and now I can calculate A, correct? I can calculate A by doing simply A inverse K. Oh, sorry, K inverse F. So now I can calculate A is equal to K inverse F, and rather than doing it by hand, we'll go to the Matlab code and try to see how that works. In your handout, I've given you this Matlab code. I won't actually go through line by line, but I'll very quickly tell you what this does. So as it says, it can solve any one-dimensional problem which has displacement specified at x equal to 0 and some traction specified at x equal to L. Your area cross section is assumed to be 1, but Young's modulus C could be varying, body force B could be varying, anything else could be varying here. The things that the program will ask you, maybe I'll go to right here, things that program will ask you is to tell me the length of the bar, tell me the specified displacement at x equal to 0, tell me what the traction is at the end, give me a function for the Young's modulus function. If the function is constant, you have to use what I'll show you in a little bit. So maybe I'll actually run this and show you the output. Prompt, step. All right, so I'm not sure if this is visible to you in the back, but the idea is that this kind of window will pop open and you will have to specify the length of the bar, displacement at 0, traction at L, Young's modulus as a function of x. If the Young's modulus is constant, you have to actually specify a function called once times that constant. If you remember, maybe sometime back in Matlab, you had to, when Matlab expects a function, you cannot just say a constant, otherwise it gives you an error. Similarly, for body force function, I have B naught, which is 10 in this case, times sine x pi over L. The exact same problem that we were running right now. Number of divisions for the trapezoidal rule, this I'll tell you what that means. I'm saying that the bar will be divided into 100 points, and I will use that to calculate an integral. Number of polynomial terms in the Ritz method. I'm saying choose the Ritz method with 1 term, 2 terms, 3 terms, 4 terms. So what we want to do is to see what happens if I choose one term in my polynomial expression, which would be equivalent to choosing just H1. It's very similar to what we did in our review session also. The exact solution to this problem, let me ask you that, is a cosine something. Can you tell me how many terms I need to get the exact solution? How many polynomial terms do I need to get the exact solution? Infinite, right? No matter how many terms I choose, I'm not going to get there. But we'll see that if I choose 1 term or 2 terms or 3 terms or 4 terms, what really happens? Okay. Of course, we expect the solution to get better. Let's see if that happens. So back to Matlab. I'll say OK here. These are, by default, these things are already entered in this. So once I get there, now the next step, it will basically go through in here and assign all of those entries that were given. What we are doing next is computing an exact or a reference solution so that I can compare my Ritz method, my approximate numerical solution, to that exact solution. So the way I'm doing that, you can see right here, this part, I'll go back to the Matlab code here. This part of the code, this is basically where I'm doing integral d sigma between sigma x to sigma L is equal to integral between x and L of minus b dx, and I don't need the constant. Right? Since I don't need the constant, I can evaluate these integrals by doing numerical approximation, which actually tells me that sigma x would be equal to sigma L plus integral x to L b dx. Okay, this integral x to L b dx, this is an integral that I can calculate by doing numerical integration. If my bar is of length L, let's say this is x, this is body force function b of x. In my current case, my body force function is like that half sine wave. What I'm saying is that I'll divide my bar up into those 100 divisions, as I said, calculate the height of each of these rectangles, because I know the body force function, and then I'll sum up the height of these rectangles, and that would be the integral b dx. That would immediately give me a function for stress. Make sense? All I'm doing is integral b dx in that blue bracket in that Matlab code. Okay. Once I have stress, I will do the same sort of integral for the displacement. Here is where I'm doing integral u between u0 and ux is equal to sigma x over c integral dx between 0 and x. So both of these integrals give me some exact or very close to exact reference solution to compare my approximate Ritz method solution. So let me do that. After this point, so I'll put a breakpoint here, and hopefully you're all familiar with how to use breakpoints in Matlab. This is a very good tool to help you understand how things would get computed. Let's see what that looks like. This is the exact solution that was given by the user, just so that I can compare it against my Ritz method. This is the axial displacement on the left. Okay, length of the bar was 10. The tip displacement is around 0.4. Okay, clearly it's a non-linear, obviously, but it's a function that is given by that exact solution, cosine and all of that. This cannot be approximated with polynomials exactly. The axial stress is given by this function, maximum stress at left, and 0 or 10 is the amount of stress at the right end. All right, so this is the reference solution that I've just plotted. Let's now compute the Ritz method solution. So for Ritz method, I'll start from here, step, step, step. Now n Ritz, this vector, Ritz vector is 1, 2, 3, 4. This is saying that repeat the Ritz solution for 1 term, 2 term, 3 term, 4 term. So let's do the Ritz solution for 1 term and see what happens. I have the K stiffness matrix, the F vector, and both of there are these loops, for loops, these nested for loops. What they will do is calculate this K stiffness matrix I comma j term, exactly the integral that we did by hand, and it will calculate the F ith term. And at the end of this loop, I will add the traction as well. And what I'll do is I'll go to this point. At this point, I'm just doing A is equal to inverse K times F. And just as a side note, we usually do not do inverse of a stiffness matrix because inverse is much more computationally expensive. It takes longer. So instead in Matlab, this backslash function is the one that actually, when you use it, it means K inverse times F. Okay, and at this point, for 1 term, I have the F vector. 1 term means F would be 1 cross 1, 41.8 in this case. What would be the size of K? also 1 cross 1. So K in this case is 100, and that immediately gives me the solution for A, that's 0.4183. I plug that back into the original approximation. Ritz is equal to H0 plus A times X, right? Hopefully you see that this is the X function, this is the A matrix. And at that point, I'm ready to plot the Ritz solution. So I'll go to this point directly. Let's see what that plot looks like. For the displacement, I get this blue line. It's a straight line, no surprise there, because we chose a linear function, right? The derivative of the straight line linear function is a constant, no surprise there as well. What I'm plotting here in the bottom is the difference from the exact solution, okay? So clearly the displacement values you can see are up to 0.4 or 0.5. The difference are 0.01 or 0.1 here. Differences in the stresses, this is essentially the bottom two plots are the errors in displacement and errors in error in stresses. So if I use one term approximation, I get a fair bit of error. 0.1 error out of 0.5, that's like 20% error in displacement, right? All right, so that's my one term approximation. I'll go back now to the loop starting, and now I'm choosing n Ritz equal to 2 terms, quadratic approximation, okay? I'll go through the same exercise, calculate my F vector. F vector is now 2 cross 1. Calculate my K matrix. K matrix is 2 cross 2. And again do K inverse times F. I get my unknown coefficients A, which would of course be 2 cross 1. These are the coefficients for H1, coefficient for H2. Okay. Plug that back in and plot the solution. Let's see what we get. We get this green curve. Very, very close to the exact solution. Okay. And if you look at the error in displacement, it's very minor, right? Similarly, if you look at the stress plot, this was a quadratic function. The derivative of that quadratic function is going to be a linear. So green line here is straight. Okay. And the error in the stresses is also what you're seeing here. Similarly, so if I do the same exercise with 3 terms, then F, the vector F is a 3 cross 1 now. The matrix K is a 3 cross 3 now. Calculate A again and plot the cubic. So this is H1, H2, H3 up to cubic terms. You don't even see the green curve. Why? Because the red curve is right on top of the green curve. That the cubic solution did not improve over the quadratic. Can anybody guess or tell me why? The coefficient of the cubic term is 0. Why is that? And actually, I'll show you that. A0, it's very small, it's surprising, but it should be actually exactly 0. But the reason is that if you look at the exact solution, it's a cosine type term, right? Cosine can be approximated with the 1 plus x square plus x to the 4 and so on. So it should not get any contribution from x to the power 3 terms. So that's why this cubic term does not improve the solution at all. Now the last thing would be to do the x to the power 4 term. If I add that, then my F vector is 4 cross 1, K matrix is 4 cross 4, and the Ritz solution for unknown coefficients is 4 cross 1. Surprising why this is. Maybe I'll check that and let you know, but let's plot it and see. In this case, what we get is this pink curve where you can see that the error of the pink curve is extremely small in displacement. And the pink curve is even closer to the exact solution. And finally, I'll let it run the solution through. And what we get is this. You might think that the pink curve has no error, but It's actually very, very small error, even in displacements and in acceleration. So you can see clearly that if you keep on increasing the terms, polynomial terms, you get closer and closer to the exact solution. But in this case, you will never get to the exact solution because the exact solution is a cosine something. Okay. All right. So let's stop here, and then I'll continue off on Monday. And of course, we'll meet in the review session today at 3:30.